In this session, we will study Gauss law. So Gauss law states that the net outward electric flux through a closed surface is equal to the charge contained in the volume enclosed by the surface. Let us consider a closed surface. So let's say this is the closed surface. Let us consider a differential surface ds on this surface. Let's say at this point the flux density is given by this. So the flux that is emerging from this differential surface is given by the dot product of d and ds. So here d psi is the differential flux emerging from the surface, differential surface ds. So the net electric flux which is emerging from the closed surface is obtained by integrating this d psi over the entire closed surface. This circle indicates that it's a closed surface. So this is the flux emerging from the closed surface. And let us say the volume charge distribution within this closed surface is given by, let us say, rho v. So here the charge enclosed within this volume enclosed by the surface is given by volume integral of rho v throughout the volume enclosed by the surface. So Gauss law states that the flux emerging from the closed surface is equal to the charge enclosed within the volume that is enclosed by the surface. So this is the integral form of Gauss law. Let us consider this example. Here we have two surfaces, closed surfaces S1 and S2. So let us say we have a charge of 5 microcoulomb here, some 2 microcoulomb here, then here some -4 microcoulomb, and then some 7 microcoulomb. So here the flux that is emerging from the closed surface S1 by Gauss law, it is equal to the net charge which is enclosed within the volume enclosed by the surface. So therefore the net charge here is enclosed by S1 is 5 microcoulomb and 2 microcoulombs. So it is 7 microcoulombs. Whereas the flux emerging from the surface S2 is equal to the net charge enclosed. So in this case it is +7 -4 and +2. So therefore it is 5 microcoulomb. Before deriving the proof for Gauss law, we'll briefly discuss about the concept of solid angle. Suppose, let us consider a surface ds, which is shown here. Let us consider a point O here. So we want to find out the solid angle subtended by this surface at this point O. So let us construct a sphere of radius 1. So here this is a sphere of radius 1. So the solid angle is defined as the area on this unit sphere whose center is at O, and this area subtended by this surface ds. So this is known as solid angle. See, for example, here this is the surface ds, which is subtending an area d omega here, and this d omega is a pattern of the surface of a sphere of unit radius whose center is at the point O. So to determine this d omega, we can obtain a projection of this surface ds on a plane which is normal to this radial line drawn from the center O. So this area is ds cos theta. So here uh, theta is the angle made by the normal to this surface ds with the radial line. So here this area is ds cos theta. So we can see that this ds cos theta, that is the ratio of ds cos theta and d omega, is given by r square by 1 square. So therefore d omega is given by ds cos theta divided by r square. To derive the proof for the Gauss law, let us consider this closed surface which is enclosing a point charge q. Now the flux emerging from this closed surface is given by surface integral of normal component of d over the closed surface. So here at this point, this surface ds, here is the surface ds, and of course this is the direction of ds, and this angle made by this ds with respect to the radial line which is drawn from the point charge q. So from this figure we can see that d dot ds is given by d into ds into cos theta. From this figure it can be seen that the flux density d at this point due to this charge q is given by d is equal to q by 4 by r square. So therefore substituting this 2 in 1, we get q by 4 pi r square to ds cos theta. That is over the closed surface. So here q can be taken out, and we have ds cos theta by r square over the closed surface. So you can very easily see that this ds cos theta by r square is the solid angle subtended at this point charge by the differential surface ds. This integral is the total solid angle subtended at this point q by the entire closed surface. So which is nothing but it is the area on the surface of unit sphere with center at this point. So obviously the area of this surface of this sphere is 4 pi. So therefore the total solid angle subtended by this arbitrary closed surface at this point is given by 4 pi. So therefore we have q by 4 pi into 4 pi, which is equal to q. From this we can observe that the net flux which is emerging from this closed surface, that is psi, is equal to the net charge which is enclosed by the closed surface.